I think we have discussed the Laplace transformation of the integral in the last class, and we have done two problems, worked out problems. Now we come to the problems on differential equations, because we have already studied method of finding Laplace transformation of derivatives. So using that derivative we can find the derivative of the Laplace transformation of the derivative, we can find the original function. That is the beauty of this Laplace transformation application. Okay, if we have the differential equation like this, y double dash second derivative y double dash plus ay dash plus by equal to r of t, and initial values are given. What are the initial values? V of 0 equal to k0, y dash of 0 equal to k1. Okay, so this is the initial value problem. I think the students from the mathematics background might have studied in detail about the differentiation equations and method of finding solutions. In this book, it means the advanced engineering mathematics, you can see some chapter on this finding solution of differential equations. I have studied in degree classes based on this book. In mathematics degree, you can see there is a paper on differential equation, and the reference book of that paper is nothing but this is advanced engineering mathematics. So that is the reason I have chosen this book for the study of this Laplace transformation. So differential equation. So this is the typical problem of initial value problem of differential equation. Here we have only first derivative and second derivative. So we have a variety of methods for solving this type. This is an alternative method. The Laplace transformation. This is an alternative method for solving differential equations. Okay. First of all, we have to find out the Laplace transformation of this equation, y double dash plus ay dash plus by plus r of t. So when we apply the Laplace transformation operator, you can see that this is s square into y of s. Y of s means L of y. Laplace transformation of y, s square into y of s, y minus s into y0 minus y dash of 0 plus a into Laplace transformation of y dash, that is nothing but s into y of s or L of y minus y of 0 plus b into Laplace transformation of f, that is y. This is equal to r of s. R of s is nothing but Laplace transformation of small r of t. Okay, so this is the formula after applying the operator, Laplace transformation operator. Okay, so we can pull it together. So we can take the similar terms as a group, that is s square plus as plus b into y. That is actually a quotient of y. So y s square plus as plus y into y equal to, in the right side, or we can move to the right side. So we will get s plus a into y of 0 plus y dash of 0, okay, plus r of s. This is a usual mathematical operation. There is nothing new with this. Okay, only basic numerical operations is done. So we can divide. We have to find out the value of y. So we have to divide with s square plus as plus b on both sides. So you will get what is that? Y equal to s plus a into y0 plus y dash 0 plus r of s divided by s square plus as plus b. That is not given here. At the same time, you can think about that. And let us denote q of s equal to 1 by s square plus as plus b. So that can be factorized as like this. That is 1 by s square plus as. So we can add one term, that is 1 by 4 into a square is added and it is subtracted, 1 by 4 into a square. So what will be the result s square plus as plus 1 by 4 into a square minus 1 by 4 into a square plus b. So first three terms are combined together, so you will get s plus this can be considered as 2 into a by 2 into s, that is nothing but as 2 into a by 2 into s, so 2ab form. Okay, so 2 into a by 2 into s, so a by 2 is come here. Okay, so s plus a by 2 all square plus the remaining term b and the subtracted term, that is 1 by 4 into a square. So that can be, so you can consider this form. So what will be y of s? Y of s will be, what is that? Y of s will be, so it is considered as q of s. So s plus a into y naught divided by s square plus as plus b, that is s plus a y naught into q of s. Again y naught y dash of 0 divided by s square plus a square s plus b, that is y dash of 0 into q of s. So that is combined together and it is given here. Okay, and last time r of s divided by s square plus as plus b, that is r of s by r of s into q of s. Okay, that is written here. Now consider the initial value problems. If y and we assume that y of 0 equal to y dash of 0 equal to 0. We assume that y of 0 equal to y dash of 0 equal to 0. So we will get y of s equal to r into q. Okay, or q is equal to that. That's just rearrangement. So y is equal to r into q if and only if y of 0 equal to y dash of 0 equal to 0. Okay, so this is a particular case. We cannot ensure always y of 0 equal to y dash of 0 equal to 0 always. It is a special case. Okay, in that special case you can see that y is equal to r into q. And how can we find out the inversion is that we apply for the inversion of y. And so let us look at one example. And we will consider more complicated problems in the later session by using some more results. Okay, that we will discuss in coming classes. So consider this example y double dash minus y. So first derivative is not here, so that means the quotient of that first derivative will be 0. So y double dash minus y equal to t. So here small r of t is equal to small t. Okay, what is b? A is 0, b is minus 1. R of t is equal to t. And the initial values are given. So here look at that, y of 0 is 1. So not 0. Y dash of 0 is 1. It's not 0. So this is the step 2 conclude with the solution with for y of 0 equal to 0 and y dash of 0 equal to 0. Same time you can come to the step 7, equation number 7 for any case. So in the case after 7 you can see that is a special case, and in this example it is given that y of 0 equal to 1, y dash of 0 is equal to 1. So let us find the Laplace transformation of this differential equation. So what will be that? L of y double dash minus L of y equal to L of t. So L of y double dash, what is that? S square into y minus s into y 0 minus y dash of 0. Okay, what is L of y? That is y. So what is L of t? That is 1 by s square. So you can again simplify like this, s square minus 1 into y. The quotient of y is nothing but s square and minus 1. So s square minus 1 into y equal to 1 by s square is there, and you know moreover this is minus s into y 0, that is minus s, y dash 0, that is 1. So when we move to the right side it will become s plus 1, and it is already 1 by s square is there, so we can see that it is s plus 1 plus 1 by s square. Okay, that is trivial mathematical technique. So we can again what is q? You can find the q from here. So 1 by s square minus 1 is q. So but q is equal to 1 by s square minus 1. So you can see y is equal to s plus 1 into q plus 1 by s square into q. So that is s plus 1 by s square minus 1 plus 1 by s square into s square minus 1. But you know that s square minus 1 is s minus 1 into s plus 1. So that can be s plus 1 can be cancel each other, and so the remaining 10 will be 1 by s minus 1. And this in this step, in the second step, you can see that 1 by s square into s square minus 1, that can be right like this. S square minus s square minus 1 divided by s square minus 1 into s square. That is nothing but 1 by s square into s square minus 1. So that can be modified like this. So that is a trivial mathematical technique. That's only okay. So y is obtained like this, and now we move to the this is a Laplace transform of the function. So what is the function? This is a Laplace transform of the function. That is, you don't know what is the function, but you have to find the function. So how can we find it? Find the inverse. So y of t is equal to L inverse of y. L inverse of, so that can be substituted, that is L inverse of 1 by s minus 1 plus L inverse of 1 by s square minus 1, that minus 1 by L inverse of 1 by s square, that is non-results. Okay, what is L inverse of 1 by s minus, that is 1 e raised to t. Second one is sin ht, third one is t. So that is written like this. So this is a illustrative example. And you can see another example here. So y double dash plus y dash plus 9y equal to 0. Initial values are given. Y of 0 is equal to 0.16. Y dash of 0 equal to 0. So apply the Laplace transformation on both sides. You will get s square L of y double dash, that is s square into y minus 0.16 into s plus s into y, plus L of y dash. What is that? L of y dash is not given. So this is the simplified equation, I think. L of y dash will be the third term of for the first term becomes 0, so that will be sy minus 0.16. and what is L of 9y? That is 9y. Okay, so you can take the similar term, that is s square plus s plus 9 into y, that equal to 0.16 into s plus 1. So that solution is y is equal to 0.16 into s plus 1 divided by s square plus s plus 9. Okay, that equal to 0.16 into s plus 1 by 2 plus 0.08 what is it, right, divided by s plus 1 by 2 square plus 35 by 4. Okay, so you can apply the shifting theorem. It is the shifting is minus 1 by 2. Okay, minus 1 by 2 here, and moreover you can see that this is you can split this one. Okay, you can split this like 0.16 into s plus 1 by 2 divided by s plus 1 by 2 square plus 35 by 4 plus 0.08 divided by s plus 1 by 2 square plus 35 by 4. We can review that formulas. What are the formulas for cos and sine? You know the formulas. Okay, for cos it is s by s square plus a square, and for sine it is a by s square plus a square. This is shifting theorem. S minus a, yeah, look at here, s minus a divided by s minus a square plus omega square. Instead of omega we have 35 by 4, so omega will be root of 35 by 4. It is given here. You can look at these formulas, these two formulas, e raised to a t cos omega t e raised to 80 sine omega t. So we can apply that formula and so applying this formula, you can see that this is the first term, e raised to 80 into constant is there, cos omega t, plus e raised to 80 into constant is there, sine omega t. Omega is root of 35/4. So that is simplified here. Okay. So what are the advantages of Laplace method? So you have to think about the application. Solving a non-homogeneous ordinary differential equation does not require first solving the homogeneous ordinary differential equation. So we have in the first problem we have seen the non-homogeneous ordinary differential equation. Okay, but in the traditional method you have to for getting the solution of non-homogeneous ordinary differential equation, you have to first of all solve the homogeneous. That means you have to take the right side 0 and then solve and then apply again using some method is there. And first of all you have to find the solution of homogeneous ordinary differential equation, and then you have to move to the non-homogeneous methods. But in the Laplace method you don't think about the homogeneity or non-homogeneity, you can directly go to the solution. Okay. Initial value is automatically taken care of, and complicated inputs R of t can be handled very efficiently. So in the non-homogeneous ordinary differential equation, it is very difficult to solve when the R of t is complicated. Okay, R of t is in the complicated form. So but in the Laplace transform method, even if it is complicated, you can solve easily. Okay, we have tools for solving this type of complicated situation. Okay. This is another problem, you can skip that. So anyway, you have to do all these problems from equation, the problem set 6.2. You may do all these problems, and if you have any if you do all these problems, you will be practiced very much, and you can solve or you can apply the Laplace transform method in your real life applications also. So you have to you may try to solve all these problems using the available technique and using the available knowledge. And if you don't have any much knowledge in trigonometric equations or in differential equations, you refer this book itself. Okay, in this book you can see the method of solving differential equations. Some trigonometric formulas are given, and you can refer also the +2 mathematics book. That is in that book I think it is the trigonometric equations are given. Okay, many trigonometric equations are, you require that trigonometric equations, so you have to study based on the +2 book and this book. Okay, you can solve all these problems 23, 24, 28. I think you need only 1 hour for solving all these problems. In my degree classes I have solved all these problems. So that is the reason for getting CSR net after immediately after completing the my MSc course. Okay, my method was like this. I will solve all these problems and I will practice all the problems in the books like this. Okay, and that gave me more confidence for getting for appearing this type of examination. So that is the reason for getting CSR immediately after completing before my MSc course. And I got in the mathematics level, that means first 20 category. I was in the first 20 category. That is only because I have solved all these problems, mathematical problems, and I have done as far as possible maximum problems in my CSR test. So you have to do like this, like that. Otherwise, you cannot claim that type of examinations. victory. So that is, you can try for that. You yourself try that. Okay. Another is unit step function and the second shifting theorem. Okay. So let us look at this theorem, unit step function, second shifting theorem. Let us consider function u of t minus a, that is 0 if t is less than a, 1 if t is greater than 1, and a is a positive number. Okay. So this is the shape of that function. 1 in between, before t, after t, this before a it is 0, and it is given here. Before it is 0 and after it is 1. Okay. So what is Laplace transform of this unit function? L of u of t minus a equal to, traditionally you can solve like this: integral 0 to infinity e raised to minus st u of t minus a dt, that equal to integral 0 to infinity e raised to minus st 1 by 1 because it is 1 in the region a to infinity. It is 1 in the region a to infinity. So here it is not 0 actually, it is actually a. Okay, in this book it is 0, that's a printing mistake, no problem. So it should be from a to infinity, so then only it will become 1, u become 1, and in all other part it is 0, so that is integrated here, and it is the, so what is the result? E raised to minus a s by s. So this is the Laplace transformation of the unit step function. So we will use that unit step function in the shifting theorem. Okay. So let us look at the shifting theorem. Second shifting theorem. If f of t has the transform to capital F of s, okay, and look at this Laplace transformation we have. This is 1 by s into some f of s. 1 by s into some f of s. Okay, so that will use here. That information will use here. So let's f tilde t equal to f of t minus a into u of t minus a. That equal to 0 because we are applying u of t minus a before t minus a, and it is f of t minus a if because it is 1, u is 1 for t greater than a. So this is actually f of t minus a. Okay, has that, so it has a transform e raised to minus a is into f of s. That is L of ft is equal to f of s. Then L of f of t minus a into u of t minus a is equal to e raised to minus as into f of s. Okay, that is the result. The inverse is f of t minus a into u of t minus a equal to L inverse of e raised to minus as into f of s. Okay, so that is the Laplace transformation, and other is inverse transformation. Okay. So what is advantage? If we know the Laplace f of s, then we can try find the transformation of by multiplying with the e raised to minus as. Okay, you have to know the L of f of t, and then the L of Laplace function of f of t minus a into u of t minus a will be e raised to minus as into the Laplace transformation of the original function. Okay, that is the beauty here. So how can we prove that? So let us take e raised to minus a s into f of s. That, what is that? By definition, it is e raised to minus a s into integral 0 to infinity e raised to minus s tau into f of tau d tau. You can take that into inside, so that is integral 0 to infinity e raised to minus s into tau plus a into f of tau d tau. Okay, substituting tau plus a equal to t, then tau is equal to t minus a, that equal to d, that means d tau is equal to dt. Okay, So we obtain e raised to minus as into f of s equal to integral a to, this is we can apply here. Here we can substitute t, and here we can substitute instead of tau t minus a. Tau is nothing but dt. When tau equal to 0, t equal to a. So the integration will become integral a to infinity. When tau equal to infinity, t equal to infinity. So integral a to infinity e raised to minus st f of t minus a dt. Okay. So okay. So instead of writing integral a to infinity, we can write integral 0 to infinity. At the same time, up to 0 to a we should have 0. So we can use this function here. If we consider this function here, then the result will be integral a to infinity e raised to minus st f of t minus a. So instead of that, we can write integral 0 to infinity e raised to minus st f of t minus a into u of t minus a. So this is actually integral 0 to infinity e raised to minus st f tilde of dt. So from this we can compare with the traditional Laplace transformation formula, and we can see that integral 0 to infinity e raised to minus st f tilde t dt has that Laplace transformation e raised to minus as f of s. So what will be the inverse of this transformation? That is f tilde of t. So small f t tilde of t is equal to L inverse of e raised to minus as f of s. Okay. So I think you got the idea of this theorem. You can write it down in your notebook, and here we have one example that will be discussed. Okay, that will also we will discuss now. Okay. Consider this function f of t is equal to 2 into integral 0 from 0 to 1 f of t equal to t square by 2 into t square by 2 from 1 to pi by 2 cos t from t greater than pi by 2. So you can write this equation as a single form like this: 2 into 1 minus u of t minus 1. Okay, 1 minus u of t minus 1. And this is half into t square into u of t minus 1 minus u of t minus pi by 2. Okay, then cos t into u of t minus pi by 2. Okay, note that u of 2 into 1 minus u of t minus 1 gives f of t for 0 less than t less than 1. When this t becomes t becomes 0, or t is in between 0 and infinity, 0 and 1, then this function will be only 2. Okay, other u will be 0, or other u's will be 0, because u will be 1 only after pi by 2 for this case, u will be 1 for this case, and u will be 1 only for after pi by 2. Okay, in this case. Okay, so in between this 0 and 1, you will be 1 only for the first term. So that is why it is f of t is equal to 2 into 1 minus u of t minus that equal to 2. So that means that is f of t. Okay, so now we can apply the shifting theorem. First of all, we have to find the Laplace transformation of each and every term. So first term, take the first term. Second term. So L of 1 by 2 into t square u of t minus 1. So what will be that? So t square into u of t minus 1. That is L of, instead of t square minus 1, you can write like this. What is that? What is u of t minus 1? U of t minus 1 will be 1 if So, the t square is written like this, t minus 1 square. So t square minus 2t plus 1. So 2t plus 1. So 1 by 2 is there. So yeah, it is 2 into, it can the middle term can be considered as 2 into t minus 1 divided by 2. So we need only to add 1. Here we have we have subtracted, instead of minus 1 we have subtracted minus 2. So we have to add 1. So that term is here. Okay. So just a rearrangement of t square by 2 like this. T square by 2 like this. T square by 2 can be rearranged like this. So that into u of t minus 1. So that will be, what is the Laplace transform of this function? 1 by s cube. Okay. Not 1 by s cube. I think s square by 2. That is e raised to s square by 2. Yeah, it is the what is the equation we have applied? We applied this shifting theorem. So you will get this is actually f of t minus 1. Okay. So f of t minus 1 into what is that? 1 by 2 into f of t minus 1 into what is that? F of t minus 1 u of t minus 1. U of t. So first term is 1 by 2 into f of t minus 1 into u of t minus 1. So what is the result? So that is what is the Laplace transform of f of t? That is 1 by s 2 by s cube. 2 by s cube. Here f of t is t square, but f of t minus 1 is t minus 1 square. So what is the Laplace transform of f of t? That is 2 by s cube. So what is the Laplace transform of t minus 1 square into u of t minus 1? 2 by s cube into e raised to minus s. E raised to minus s is the Laplace transformation of u of t minus 1. Okay. And we have already 1 by 2 here. So we will cancel the 2 by s cube and 1 by 2. So we will get cube only. So 1 by s cube into e raised to minus s. So that is the first term. Second term is similarly we can apply second term t minus 1 into u of t minus 1. That is 1 by s square into e raised to minus s. And third term 1 by 2 into u of t minus 1. That is 1 by 2 into e raised to minus s by s. Okay. Similarly, you can apply this equation. Again, you can modify this 1 by 2 into t square like this. T minus pi by 2 square plus pi by 2 into t minus pi by 2 plus pi square by 8. That is a arrangement only. If you solve this, if you cancel each other and solve this, you can see that it is nothing but t square by 2. Okay. Appropriately modified this. So you can again multiplied with the u of t minus 1 by 2 into pi. So you can similarly consider this shifting theorem here, and you will get from this equation as in the similar previous step. You can see that it is nothing but 1 by s cube into e raised to minus pi s by 2, and the second term is pi by 2s square into e raised to minus pi s by 2 plus pi square by 8s into e raised to minus pi s by 2. Okay. Now what is that? Yeah, one more term is there, that is cos t in terms of cos. So L of cos t into u of t minus 1 by 2 into pi, and that can be modified like this. This is minus cos t, that can be rearranged like this, minus sine t minus pi by 2. Pi by 2 is 90. So cos theta minus 90. So that is a trigonometric formula. So we have applied that. Minus sine t pi by 2 u into t minus 1. So that is, you know, the Laplace of sine function, that is minus 1 by s square plus 1 into e raised to minus pi s by 2. Okay, we can combine together and you will get this result. Okay, so what is the final result? Final result is this one. And if you want to find out the original function, that is our aim. Our aim is to find out the function. So you can see that what is that? L of 1 by 20 t square, that is given here. That is inverse, that is sin minus, that is given here. So cos is given here, that we have already done. It is not so up to this you can see the Laplace transformation of this complicated function. Okay, what was the function? This was the function. The 2 if 0 less than t less than 1, t square by 2 if 1 less than t less than pi by 2, cos t if t greater than pi by 2. So this is a method for finding Laplace transformation of the complicated functions. Okay, we need not to find out the inverse because we have already given the function. So we need only to find out the Laplace transformation. Okay, so you can write this one also. I think this is sufficient for today's discussion, and we will discuss the application. So you can consider the problems of this section also. Okay, you may try to find out the solution for all these equations. Okay.